we are going to take a look at binary search tree. So what is a binary search tree? In binary search tree, as we know, binary trees always have two nodes. In the parent node we have one left node and one in the right node. So how are we doing that in binary search tree? So in binary search tree we have a very simple rule that left node is always smaller than the parent and right node is always greater than the parent. So let me show you an example. So this is a binary search tree. So we have 8. So 8 is greater than the left node and smaller than the right node. And here we take 3. This is the parent node. It's greater than the left and smaller than the right. So that's how every node is. For example, even this you take, it's greater than the left and greater than the right. So what do we do basically? So how do we implement this? That's what we are going to do today. Well, let's implement binary search tree and we'll do a traversal and print all the elements. We will start by creating a node. So that is the structure. We will be creating struct node star because we are going to implement this using the linked list. So obviously we have a value, right? That's what the binary search tree contains. It contains a value and then left node and right node. So basically a node contains a left and right and a value. So we'll be creating its left and right. These are because these are node star type because it will be containing a link to the left node and a link to the right node. So this link is nothing but a pointer, so we are making it of the type node star. So what do we do? First let us create a node and let's make it null. Node star, let's name it as root and we'll be assigning it null. So what do we need to do here? Basically we need to have an insert function. So I'll create an insert function and how am I going to implement this insert function? So I will create a what I will do, I will send this root to the insert function. In the insert function, before creating insert function, let's say every time I have to insert a node, okay, for this node root I will be assigning some value 8. So I need to create a node with value 8. So what I'll do, first I'll create a create node type function. So I'll have a function for create node. It does nothing but it takes the value, that is 8 or 9 or some integer value it takes, and it simply builds a node. How do we build a node? We do nothing but we create a node star, let's name it as new node, is equal to yes, this is how we do it. So we create a new node and then what we do is we assign it a value. That's what we get it from insertion. So we get this integer value, right? So we assign that value to this node, and now we have two other parameter as well, that is left and right. So we will assign them null for now. This is simply the segregation part. So we're doing nothing but segregating the nodes, segregating the functionality here. So yes, this is what it is. So I will return new node. So whenever I give an insert command, the first thing is that I need to create a new node and insert into the tree, binary search tree. So for that I will create the insert function here. So how do I create that insert function? So I'll create this of node star type insert, and here I'll take the root because I need to keep track of the parent element, right? That's why I'll keep track of the parent, and also I'll have the value here. So what I'm going to do is nothing but, let's say I get an input 8. So first I will check if my root or the first node, that is null or not. If it is null, then I will simply create a new node and send it back here. Now here I have so what I will do here, I will assign this to this. So this root will have the first node. For that condition I have to do this: if my root is equal to null, then I'll return create node of x. So what happened is basically we will be calling this create node. Here we create a new node and we will return that new node. So that node will come here and this return statement will go here. So in this route we will have a new node created with some value. So what I will do next time, so now I will create another insert statement. Now I have to insert second element. So what I will do, I need to insert 3 into my binary search tree. For that, now my node is not null. So what I have to do, I have to see whether this new node's value is less than the parent or greater than the parent. As we know the rule, if the node's value is less than the parent, then it has to go to the left node. That's how it is, isn't it? So we will check if this int x, that is x, greater than root dash value. So what do we do if it is greater than that? If it's greater than the parent, then we are going to put it in the right. Isn't that what we do? So let's do this. So we are going to do x dash right, because we will be putting low. So our right now our root is 8. So we need to put this okay, so let's say this is if this is not 3, let's say if it is 11, so we are putting it into the right side of the node. So let's say we have 11 here and this 11 is greater than the 8, so we need to assign this 11 to the x dot right. That's what we have to do, right? This new node, that whatever we got from here, we have to put it into the right side. But what we are doing is we are doing recursion, because the recursion is necessary here in this case, because let's say a long tree is there, so we need to go till the bottom of that tree and then decide where to insert that. So I'll do nothing but what I will do is I will do insert x dash right comma x. So why I am doing this recursion is because let's say we have a long tree. So I have a element and I need to insert. First I'll go to the parent and I'll see the first parent. I will show it using the picture. Okay, so let's say I need to insert a 0 here. So what I will do is first I'll go to 8 and then see whether 0 is greater than or lesser than 8. So it's lesser than 8, so I will go next to the 3. So for going to 3, what I have to do, I have to recursively call the left node. Or how do I have to do it? I have to recursively call such that the current node will be the left node. So I will insert in my function, I'll insert this, what is that, x dot right or x dot left, so that now when it calls this insert function again, I will be having the left or the right node, which is the child of the main root. So then again in that again comparison will happen, and then I will again do x dash left or right to the insert function. So I'll go again here to the child function. Then when I come to this node, I will verify whether this node is again I'll verify whether I'll make a call again to this using left or right, and then I come to a point where this node is null, because here there will be nothing here. This has no children, so this is left or right, so it's a so I will do nothing but I'll be basically inserting this node to its left or right. That's what I'll be doing. So that's the explanation for this. And then what if it is not the case? In that case I have to go in the opposite direction. That's what I have to do, right? It's a basic thing, and for that I will do x dot left is equal to insert x dash left and x. So this is what I'll be doing. This is how the insertion is. It's simple 5 lines of code. So then finally I need to return now. So I need to return root, so that after all the insertion we'll finally have to get something here, right? That's why I'll be returning this root. So let's say everything will be traversed, and final point we will be coming here and we'll be getting this root here. So that's what we are doing basically. Let's see how to explain this return root. So basically let's say I have my root node as 3 now. So after that I insert 4. So I'll come here and I'll say that my root node, that is lesser than 4, so that's 3, so I have x is 4. So I'll come here. So after this, after executing this statement, I'll call this recursively, and the recursion will come here, and in my next recursion call, this will be returned. But what about the previous call? While calling this recursion, my control will come here. After that I need to go somewhere, right? I cannot just get back like that, so I need to come here and return that, because one of my recursive call will have a return statement and other will not be having. That's why this is essential. So this will essentially be returning my root node. So no matter how many you insert, your first node will be this. So we can now it seems like our tree is created and everything is done. Let's insert some more statements, and let me insert few more nodes. So let me insert 3, and let me insert root dash 22. So now how do we verify that our binary search tree is working? We have to do something. So what we can do is we can implement a search algorithm or a traversal algorithm basically. So let's implement in-order traversal. In-order traversal is nothing but we just go to the how do we call it in-order traversal? It's nothing but increasing order. So we always do left, right, and then left, parent, and then right. So it will always be increasing order. So we can see if the result of this in-order traversal is increasing order of the values. So I'll be sending this root and I'll write the code here. In-order traversal logic. It's very simple, guys. It's very simple. So I'll make it void type, and then what I will do, in-order traversal node star root. So how do we do this? It's basically a traversal algorithm where we need to go to the left, then parent, and then the right. That's how we have to traverse it. So let me start here. So if root equal to null or root not equal to null, then only we are doing the traversal. Otherwise, if the root is null, then there is no tree, so you do not need to do any traversal. So here what we are going to do is, here let's say we do in-order traversal root dash left. This is what we are going to do. First statement will be we need to go left. Let's say we have a big tree, so this root will be our parent element. For example, if this is the tree, binary search tree we have, this root will be 8. So what we need to do, we need to start from 1 here, because we are going to do an increasing order traversal. So we need to do type print 1, then 3, then 4, then 6, then 7, then 8. So how do we do this? So we go to the leftmost node. So we do this recursion. Here will be, then we will be calling this same function with the left node as the root. So we will be getting 3, then again we'll be calling it with the left, then we'll be getting 1. So once this is null, this left of this is null, then we print this. So that's what we are going to do basically. So now we have reached the leftmost segment, leftmost node. So we are going to do cout root dash value. We'll give a space so that the code will be neat. Then what do we do? Then what we do is, then we travel the right. I'll explain why is it that done. So now we have printed 1. So what do we do next? We need to print 3. So once it is the control is at once, then how the recursion basically acts is, we know recursion uses stack. So as we know recursion uses stack, after this one the control is popped now. So popped means this will be out, then the control will come here, because we'll be pushing this 8. First I'll be pushing this 8 to the stack, recursion stack, then I'll be pushing 3 into the recursion stack, then 1, then I'll be printing 1, then I'll be popping this. After popping this, I'll be going back to 3 now. So now I'll be printing 3 immediately, because once I'm in 3, my recursion acts in such a way that it immediately prints 3. Then what I do, I go to 6. After going to 6, my again the condition is such that I go to the left. That's what my basic condition is. If there are no more left, then I will print this element, then I'll go right. That's how it is, right? I'll go to the left. If there are no more left, then I'll pop it, then I'll come back here, then I'll print it, then I'll go to the right. That's how I'm doing. That's how the basic logic is. It seems very simple. That's how it is. So let's see if any errors are there. It seems like we have a couple of errors, so let's go and fix each and every one of them. So this is good because we can understand where we have made actual mistakes. So one I can see here, after the structure we have not put a semicolon, and then this insert node. So insert is a function, so we cannot use just insert anywhere. So I need to make this insert node. It's in C++, and there are in multiple programming language, just insert is a it's a function, or it's a standard keyword which cannot be used. So we will be using that, and I'll again compile my program and see for errors. We have few more errors. Oh, what I have done, I have done struct node star. This is a fault, right? This is a major problem. So it's just struct node. The syntax is it is a syntactical mistake that I have made. I might still have some more errors. Obviously I did expect some errors because obviously this is not a simple code to go at one go. Wow, I have missed new keyword here, and instead of root I have used node. Yes, while making I do make mistakes while talking and coding. So this is one error, and then other error is this, obviously I have to replace this by new node. So as we make a lot of mistakes, it helps us go to a situation where we will be able to debug all of them, and we still have errors. I guess these issues are because I have not declared the type of node in the function. I hope this is the other error, and I guess we should be good to go. Let's hope so. And well, finally few errors. We're not seeing many errors now. Okay, again instead of no root I have made x dash, right? Wow, so many mistakes I made. So this is root. X is my integer value, so I'm not touching that. I'm just making changes with my root. That's all I'm making. Let's see this now. Okay, two issues finally here as well. I guess we made quite a few errors here, but as long as learning is concerned, we're good. So let's see what is compiled. Yes, there we go. We finally have the beautiful output: 3, 8, 11 and 22 in the increasing order. That's how binary search tree is. Pretty simple, but we might make mistakes, but we will debug them and solve them as well.